Welcome everyone to our talk by the student of origin. We have Swarnalipa today, and she will be talking about Fourier-sparse Boolean functions.
I don't have memory. What was the previous?
Hello everyone. So today I'll be talking on Fourier analysis of sparse Boolean functions over certain Abelian groups. This is a joint work with Saurabh Chakravarti, Pranjal Datta, Arijit Ghosh, and Shavato Sharma. So let me first state what a Boolean function is. So Boolean function is a function from -1 + 1 to the power n to ±1. Let's look at a few examples. So the first one is AND of 2 bits. And so it takes the value -1 when both the bits are equal to -1 and it is 1 otherwise. The second, so this is the truth table of AND function. The second one is the majority of 3 bits. It takes the value -1 if -1 occurs more than 1 and it is 1 otherwise. So if you look at the truth table, you can see that. So the first row has all 3 bits equal to 1. So it takes the value 1. The second row has 2 bits equal to 1 and 1 bit -1. So it takes the value 1 and so on. So now I'll define characters. So the characters are monomials, which are of the form x1 to the power r1, so until xn to the power rn, where so xi is so x is equal to x1, x2, xn, so that is from -1 + 1 to the power n, and ri's are from 0, 1. So as you can see, these characters also are Boolean valued. So they also take the values either -1 or +1. And 2, so this function that I have already defined earlier, that is AND of 2 bits, that can be written as a linear combination of these characters. So AND 2 can be written as half plus half x1 plus half x2 minus half x1, x2. And another thing to note is that the coefficients here are not integers, but the function takes the value -1 and +1. So so this is the truth table. And yeah, so the second example that I stated earlier, that is majority of 3 bits, that is also that can also be written as a linear combination of the characters. And so this is the this is how majority can be written. So it is half x1 plus half x2 plus half x3 minus half x1, x2, x3. Again, here also the coefficients are not integers, but the function evaluates to ±1. And also number of characters is equal to 8. But not all the characters are present in the polynomial expansion. So this is the truth table again. As you can see, it evaluates to ±1. So it turns out that this is not the property of AND or majority. This is in general true. Any Boolean function can be written as a linear combination of the characters. And the values are second roots of unity, that is, they are either -1 or +1.
Values of what?
Values of the characters. And these characters have some nice properties. So they are orthogonal to each other with respect to this inner product. And the inner product is equal to 1 if r is equal to s, and it is 0 otherwise, which shows that they are orthonormal to each other. Not only that, they form an orthonormal basis for the vector space of functions. minus 1 plus 1 to the power n to r. And the set of characters minus 1 plus 1 to the power n, it is denoted by hat of this thing. And they also form a group. So I stated earlier that any Boolean function can be written as a linear combination of the characters. So this theorem states that they can be uniquely written as a linear combination of those characters. And the corresponding coefficients, they are called Fourier coefficients. So f at chi r over here denotes the Fourier coefficients. And the Fourier coefficients are given by this formula. So it is 1 by 2 to the power n summation fx chi r x, a summation over all x. And I have just written, so chi r x is x1 to the power r1, so until x n. And Fourier sparsity is the number of non-zero Fourier coefficients of f. And Fourier support is the set of all R for which the corresponding Fourier coefficient is non-zero. So Fourier sparsity is basically the size of the Fourier support of f. So now let's look at again at AND of 2 bits. So these are the characters of AND. 1, x2, x1, and x1, x2. And this is how AND can be written as we had seen earlier. And Fourier coefficients are therefore, so f hat of chi 0, 0, that is the constant coefficient, that is equal to half. F hat of chi 0, 1 corresponding to the x2, so that is half. Similarly, this is half, and the last one is f hat of chi of 1, 1, that is corresponding to x1, x2, and that is also, that is equal to minus 1. So here, as we can see, the Fourier sparsity is equal to 4. All the coefficients are non-zero. Now comes the majority. So majority is again, so recall that majority is the function which takes the value minus 1 when minus 1 occurs more than 1 and it is 1 otherwise. And the characters are, so similarly, the characters are 1, x1, x2, x3, x1, x2, x1, x3, and so on. So we have 8 characters in total. But the polynomial expansion of majority has only 4 characters. So half x1 plus half x2 plus half x3 minus half x1, x2, x3. Hence, Fourier sparsity is 4. So although we have 8 characters, the sparsity is equal to 4. So now comes the indicator function. So I'll just define it so that, so I'll define some other function later. So it will be easier to understand. That's why I have just defined it. So indicator function at a point is given by, so indicator function at a is the function which takes the value minus 1 when x is equal to a and it is 1 otherwise. And the Fourier coefficients are given by this. So as you can see, all the coefficients are non-zero in this case. And hence the sparsity is 2 to the power n. So now comes the addressing function. So this function, it is defined from minus 1 plus 1 to the power log t plus minus 1 plus 1 to the power t. And it takes the value y binary x, where binary x is the integer whose binary representation is given by x. So, and addressing function can be written like this. That is just summation over will be identity into y binary b. So Fourier support is given by this set. So it is r comma s, where r is from the first part, that is minus 1 plus 1 to the power log t. And the second part, so all those a's for which, so all those a's such that a's has only one bit non-zero. and hence Fourier sparsity is equal to 2 to the power log t into t, which is t squared. So these are quite a few examples of Boolean functions. So, another thing, so there are quite a few nice properties of functions, of those functions which whose range is equal to -1 plus 1. And so, so this is the Parseval's theorem for whenever the range is -1 plus 1. So Boolean-valued functions could also take, so this could be the, so 0, 1 could also be the range of Boolean-valued functions, but the range is plus or minus 1. Whenever the range is plus or minus 1, then it turns out that the sum of the square of the coefficients is equal to 1. So this is one of the nice properties that the functions have. Another property is granularity. So how small can the non-zero Fourier coefficients be? So can they be very close to 0? Gopalan in the year 2011, Gopalan et al., they showed that the non-zero Fourier coefficients are actually integer multiples of 1 by sparsity. So they cannot be very close to 0. This is the corollary. So since they are integer multiples of sparsity, so the non-zero Fourier coefficients, they are always, the absolute value is always greater than equal to 1 by sparsity.
But here I should think of the function as going from 0, 1 to the end to plus minus 1.
No, that is also -1. So yeah, both the cases are okay. So it is true for both.
No, it's 0, 1 to the end, but the characters are still -1 to the product of the x-axis.
Yeah, the question of what do you think of C2? C2 is plus minus 1 with multiplication take the group operator.
So yeah, so this is what Gopalan defined to be, Gopalan et al. Defined to be granularity. So granularity, so a rational number is called k granular if it is of the form some integer by 2 to the power k, where k is some positive integer. So from it follows from the previous theorem. So sorry, so basically the Fourier coefficients are logs, ceiling of log sparsity minus 1 granular. From there it follows that they are integer multiples of 1 by sparsity. So if you put k equal to this thing, that is ceiling of log sparsity minus 1, then you will get sparsity.
You won't get sparsity, you will get the closest power of 2.
Yeah, so that is also, yeah.
Okay.
So I mean, any like it cannot have. I mean, so it has to be one. It has to be some integer multiple of inverse power of 2 always.
Yes.
But sparsity need not be a power.
No, sparsity.
Is it always that it's a power?
Yeah. No. So sparsity needs to be a power of 2 actually. Yeah. Sparsity is a power of 2.
Yeah, that paper it does say that it is a power.
Yeah.
It has to.
Yes, it has to be a power of 2, yes.
No, but it has to be at least a multiple of a power.
Yes.
Or
No, 1 by, yeah.
on one hand, I mean,
Just not saying it.
Yeah, I don't see also, but I can imagine the same kind of argument that shows that.
I mean, every Fourier coefficient denominator will be a power of 2.
Yes.
Right.
Yes.
And the other one is
Because it values to 1, no, but still, okay, it values to 1 minus 1. I'm not seeing it, just blathering it.
No, is this not true that every coefficient has to be a?
That's the theorem.
That's.
No, every coefficient has the denominator is the power of 2.
Oh, yeah.
Yeah, that's because it's an
The Fourier
expectation.
coefficients are, yeah, the Fourier formula.
Yeah, and the previous theorem says that, if you have sparsity s, every Fourier coefficient is a multiple of 1 over s. Which means that has to be a power.
Yeah, together they will imply that, but
Yeah,
okay, so this is, yeah, but
There's no theorem. That's all the information. I haven't got the proof of the.
Okay, with the Fourier formula and this theorem it implies.
yeah, that's
Sparsity is
what I was
power of
thinking,
two,
like, the theorem seems to imply that, SF has to be a power.
Power of 2, yes.
Yeah, that's what.
So now sparsity, yeah, so as we had seen earlier, sparsity of n is equal to 4. And for a function with sparsity 4, the Fourier coefficients should be 1 granular by this theorem. And we recall that the coefficients of n were plus minus half. And hence, and they are 1 granular. And similarly for majority, the sparsity is 4. And for the same reason, the coefficients of majority are also 1 granular. Now I'll explain things for finite abelian groups of a specific form. So let me, a finite abelian group can be written as direct product of cyclic groups, which are, so that is zp1 to the power a1 cross till zpt to the power nt, where pi's are primes and they are not necessarily distinct. And this Boolean-valued function from a finite abelian group is a function from g to plus minus 1. And this has got immense importance in theoretical computer science and mathematics, and people have studied this in additive combinatorics and cryptography. So here we have proved our results for finite abelian groups, which are of the form zp1 to the power n1 plus till zpt to the power nt, where pi's are prime and they are distinct primes. So yeah, and also observe that z2 to the power n is also a finite abelian.
But not where your result applies.
Sorry?
No, no, it's fine. It's fine.
No.
Here you're assuming that the p's are, it's because, there's no higher powers.
Hmm.
No, so, okay. What was your question? No, there the p's aren't necessarily distinct. Usually, when you write any abelian group as a product of cyclic groups.
Yeah.
But here you're assuming that all the periods are, basically there is nothing of prime power period. So, there is no reason, here you might as well assume that the p's are all distinct. Because if two p's are the same, you'll just combine them.
Yeah.
Yeah, I just missed that.
The thing is that the m's are gone. The m's are gone, all the m's are gone.
Yeah.
So this is a truth table of a Boolean valued function from z3 squared to plus minus 1. So it takes the value minus 1 and plus 1. But if can be expressed in this manner. So here omega 3 is the cube root of unity and hence a complex number. And so this is the polynomial expansion, Fourier expansion of f of x1, x2. The interesting thing here is that although complex numbers are involved in this expansion, the function evaluates to plus or minus 1. Here also. So yeah, so what is the character in this case? So in this case, so in case of ZPN, so from now on I'll explain everything for ZPN to make things easier. So a character can be written, so a character is defined to be omega p to the power r dot x. Here omega p is the pth root of primitive pth root of unity. And r dot x means component-wise sum of component-wise product of r and x. So characters are also complex numbers. And so in case of Z3 square, the characters are all of these. So omega 3. So you can just have a look at this. So let me go back. So omega 3 to the power x2, 1, omega 3 to the power x2, omega 3 to the power 2x2, omega 3 to the power x1, and so on. These are the characters over here. And the set of characters of ZPN.
So these are. Wait, what is one? There's something missing, right? Where is 2x1? So just a type. Oh, it's there. Okay. Okay.
So the set of characters of ZPN, it forms a group, and it is known as the dual group of ZPN, and is denoted by ZPN hat. And any character can be written as a product of characters of any character of G can be written as a product of characters of its individual components. So that is the character of G can be written like this. So omega p1 to the power r1 dot x1, so until omega pt to the power rt dot xt. This is how a Fourier transform is defined in case of zp to the power n. So Fourier transform, f at chi r is equal to 1 by p to the power n summation over x fx omega p to the power minus r dot x. Okay. R dot x is again the sum of component wise product of r and x. So here also a function can be written as a linear combination of the characters of zp to the power n. So it is not only true for z2n, it is also true for zpn, and hence for G also. So not only that, they can be uniquely written as a linear combination of these characters, and the corresponding coefficients are called Fourier coefficients. So recall, so in the previous example, this is what the Fourier expansion was, and the coefficients are given by this. And Parseval's theorem is also true over here. That is, sum of the absolute value, square of the absolute value of the Fourier coefficients is equal to 1. So we take absolute value because, so in this case, the coefficients are complex numbers.
This is the magnitude.
Yeah, magnitude of them. And Fourier support is the set of all characters corresponding to which the coefficients are non-zero. And Fourier sparsity is the number of all non-zero Fourier coefficients of F. So Fourier sparsity is the size of the Fourier support. So yeah, so the main challenge comes while we define granularity for G. So in that case, the coefficients were real numbers. In this case, complex numbers are involved. And so recall the definition of granularity in case of Z2. So a rational number is called K granular if it is of the form some integer by 2 to the power K, where K is some positive integer. And also, so in this work, we have generalized the following theorem by Gopalan et al. And so which states that Fourier coefficients are seeding of log sparsity minus 1 granular, that is their integer multiples of 1 by sparsity.
So you have the ZP, right?
No, this is for, sorry, this is Z2. Sorry,
Z2.
Z2, sorry. Yeah.
You haven't yet stated your generalized result.
No, I haven't yet stated. Now note that the characters are complex numbers over here, and so again, so how can one define granularity over here? So this is how we define granularity. So a complex number is said to be k granular if it is of the form g omega p by p to the power k, where gx is a polynomial in zx and omega p is the primitive pth root of unity. Right?
So this works for groups of the form ZP to the K, but you were talking about even mixed things. No?
Yeah,
ZP1
yeah, right.
To the K1,
Hmm.
P2 to the K2.
Yes, yes, that is that. For that also this works.
But which?
So in that case, it is of some form. So it is some polynomial, so multinomial. So g of x1, x2, x.
So you will call it, they will be
Yeah.
both P to the power K as well as Q to the power K.
Yes.
Q to the power K1 and Q to the power K2.
K2, yes.
So granularity is K1, K2 is.
Yeah, so it was some yeah, p to the power k1, p to the power k2, something like that.
Okay. So the granularity will be a pair of.
Yeah, yeah, right. Yes. Yes, stop this.
Okay, very good. Okay, fine.
And generalization has been done for abelian groups of this form. So granularity, so the theorem is that the Fourier coefficients of f are sealing of log sparsity to the base p plus 1 granular.
Before you had -1, right?
And the lower bound is 1 by p square sparsity whole to the power sealing of p minus 1 by 2.
So what was the previous statement?
-1.
Oh, it's like log
Sparse.
SF minus 1.
Minus 1. Yes.
Because log s of -1, right? Granular is log s of +1 granular as well.
Hmm.
So this is a slightly weaker.
Yes, this is
Yeah.
weaker compared to your Gopalan.
That's general.
And this is the lower bound on non-zero Fourier coefficients.
And but these are both for ZP to the end, or these
Yeah.
or they can also be stated
For
to the more
for the
general.
more general thing.
So is the first theorem exactly that theorem? It is basically log. No, so what
No,
what was
that
the
base changes. So no, so the base is same and the SF to the power some 1 by t or something like that. And it goes on like that. So that I have to, I don't exactly recall, but
Okay.
logs, yeah.
Okay.
What should the thing is? Should the right answer still be log SF base P minus 1 granular? Like what?
No.
Do you have a counterexample? -1.
Yeah.
So, we have a counter example. So log sparsity -1 that I cannot say, but we have a counter example which shows that the coefficients of lower bound on the coefficients is not 1 by sparsity. So it is something bigger than, it has to be something bigger than that. So the counter example that we have constructed has a Fourier coefficient, which is some 1 by sparsity to the power 1 plus some positive thing.
That rules it out, right? That rules out sparsity -1.
Yeah, actually, yeah, right, yeah.
Because it has to be a multiple of
1 by sparsity, yes. Yeah, right. So,
Okay.
yeah,
Okay.
it actually rules out, right?
Is it a simple example?
No, I'll come to that. I have also, yeah.
actually then go back to the
Yeah.
so there you're off by a factor It's the same factor, yeah, it's the same factor. Then if I off by a factor 4, and it's the same 4 which is sort of recorded here, you're off by, I'm just setting it for p equals 2. Yeah, it's the same factor you're off by, okay.
Yes.
Also, wait, so you said it is, the lower bound is 1 over sparsity to some power?
No, it was 1 over sparsity.
The lower bound is 1 over sparsity, there is no
Yes.
power.
No,
Just-
no power. Yes.
Lower one or one?
So she
The
had.
non-zero
fun-
coefficient.
The lower one or one?
For non-zero Fourier coefficients in case of Z2n. So it was 1 by sparsity, but in this case it is something like this.
Yeah, so now it does not, it rules out -1, but it does not rule out 0.
So in the previous case, in case of Z2n, we already knew that the lower bound on the sparsity is 1 by, on the Fourier coefficients is 1 by sparsity. So the question is, can we, so I have already answered it. So it is not true. And so this is the theorem. So it basically states that there exists a function which has a coefficient. And it's so that is less than equal to 1 by sparsity to the power something 1 plus alpha p, where alpha p is strictly greater than 0.
It's a really what I think, is that to the some power. But this is. That's also weird, right? Because your gap there was just a factor of.
No, there was a power p minus 1 by 2 also.
Yes. P squared sparsity whole to the power
P minus 1
cinema
by 2.
here.
And when p is large, it looks like, I mean, it's not going to be inversely linear.
No, so I'm saying that the previous result was that the granularity is log SF minus 1 plus 1. So everything should be a multiple of
No, granularity doesn't necessarily say the absolute value is this, right? Because the numerator is allowed to be
Yes.
any integer polynomial evaluated at the root of unity. So
I
you
see.
could in principle bring the
Yeah,
absolute
actually,
value of the
yes.
complex number down,
I see.
but yeah,
Okay.
but still remain,
Mm,
yeah.
Okay, got it.
yes. This is our counter.
Just a question, so sparsity and all the Boolean case were useful for several other. So this one, so there's this Swagato's result and stuff. Do these things also translate? These results on sparsity also translate over there. So you have taken basically Gopalan et al.'s result and shown the ZP versions of those things. So do the other sort of,
So
there are some learning results and all which work when the function is sparse, when the Fourier domain is sparse, or there are multiple of them, I don't recall them. Do those also,
So-
the sparsity is still a useful thing when you work in ZP, is my question.
Yeah. So we have in this paper we have also done testing of s-sparse functions. So
Okay.
that that can be done in polynomial of sparsity and some epsilon or something like that. So it has to be some p to the sparsity to the power some p. So that kind of bound will come up. Query complexity and all. Testing sparsity, whether a function is s-sparse or epsilon power from s-sparse. So that I'll also come to. Yeah. So other results, yeah, they're. So yeah, those also should be true.
Okay.
So the thing is, we haven't checked about. So we haven't checked whether the other results are true. So Shagato's result in the sense. So are you talking about that Fourier dimensionality and sparsity?
Yes.
Yeah. So I'll come to that.
That's what we
Did not use for, yeah, no, that did not use granularity.
It is not.
Yeah, right, yes. Yeah. Yeah, right, that did not
That
use.
just follow from
Linear.
linear algebra, okay.
Yes.
That's just for any abelian.
That's for any.
The granularity is what makes these things a bit weird and.
Hmm.
Okay.
Hmm. So this is our counter example 1. It is end of thresholds. And so there exists a Fourier coefficient of this function, which whose absolute value is 1 by p to the power nc, where c is a constant and it is greater than 1. So this function has sparsity p to the power n. And so this is what, so in case of p equal to 5 and n equals to 2, this is what the value of c is.
What is it?
AT is end of this small functions, and
Like every coordinate is the second half of ZP.
Okay. Okay, there is a Fourier coefficient of 18. With absolute value is 1 over p to the n.
80 is not a delta function. It's every coordinate has to be a surface.
With absolute value is 1 over p to the n. C where c is a constant. Okay. And your value is the what is the sparsity?
Did you see the sparsity?
sparsity is p to the power n, yes.
Sparsity is p to the power.
So if I sort of embed the Boolean cube in Z3 to the n, right? So you're saying the sparsity also will be 2 to the n? No, the Boolean cube is not that. Oh, okay, sorry, 2 comma, I mean, no, 1 comma 2 to the n, right?
Not
1
1
comma 2 to the n, therefore
to
we'll have.
No, not 1 to 1 to the
That's what she's saying, right?
No, it's p is 3, then this is greater than equal to 2.
Oh, okay.
But if p is 5, then maybe you can.
Yeah.
Another thing, just a small thing to mention, that is in case of Z3, the numerator, whatever I stated earlier, g of omega p by p to the power k. So the numerator actually, it turns out that the absolute value is greater than equal to 1. In case of Z3, it is greater than equal to 1. But for p greater than 3, we don't know. And apparently it shows that it is not the case.
So does this get worse when p becomes even larger? I mean, it's like.
So actually we calculated that also, but that also comes out to be some 1 plus something which is yeah, so bigger than 0, but
Sorry, yeah, 1 plus.
yeah.
No, in the same way, is the collapse even? I mean, for example, if p was 7, should I expect this to become
1.3 or
No,
1.3 or-
no, it should be this. So it should be 1 plus something which is less than this.
Yeah, but is it more than this number or is it less than this number?
Less than this number.
Less than 1.26. Okay.
But for finite p, it is always more than 1.
So because the reason I was asking is the bound that you. Sorry, what is the bound?
So the bound was
P square is to the power p minus 1.
So how much worse does it? So suppose SF was maximum. In the sense that SF was like p power n.
yeah. So no, our result doesn't show that it is tight.
Oh, okay. Okay.
So we have just shown a counter example to show that it is not, the bound is not 1 by sparsity. This is our
Like how small the Fourier can give a lower bound, right?
yeah. Yes, right. Upper bound is 1.
Oh, no, better than that. Oh,
I don't know. It
okay.
is. Mhm. And this is our second counter example. It has a Fourier coefficient which is even smaller.
But can you ask for this question? Is there a minimum maximum for your so like the bent function? So I want to take the lowest non-zero Fourier coefficient, and how high can this be?
That we don't know. That we haven't.
Okay. Yeah, that's possibly what you're doing.
Hmm.
Yeah.
So this is counter example 2, and this has a Fourier coefficient which is even smaller than the previous one. The second one is a lack of linear independence. That is, any two non-zero distinct vectors, they are in Z2n, they are linearly independent. But in case of p greater than 3, greater than equal to 3, that is not true. For example, so taking any two, so taking these two, so the first one, the second one is a scalar multiple of the first one, and hence they are not linearly independent. And that's why, so our analysis is a bit different from what Gopalan did. And also another thing is, so is there a chalk?
It's on the plots.
So we have A0 plus A1 omega p plus A2 omega p square plus A A3 minus 1 omega p to the power p minus 1 by p to the power k, something like this. Now the thing is, whenever we when omega p is equal to minus 1, the whole thing is an integer. So in that case, it was easier to conclude that the bound is 1 by sparsity. In this case, it is not true as already been stated. So yes, it is not true because the upper portion is, so the numerator is a complex number. It can actually be very close to 0. So it was not possible for us to conclude from here that so g of minus 1 is greater than equal to 1 in this case. But for general prime, omega p is a complex number, and hence g of omega p is no longer an integer. So we cannot conclude that it is greater than equal to 1. And we use this result from algebraic number theory. It states that for g omega n where it is not equal to 0, this product of all the, so this is g omega n to the power I, so all the permutations, so take all the permutations and all.
All the
And
permutation.
permutation, I mean, so if gx is something like this, so g omega, so if g omega p is this one, then this is equal to g omega p, this upper portion. Then I am taking all of this g omega p to the power omega p to the power g and so on. So taking the product of them, then that product should be greater than equal to 1. Yes. So that I have to check again here.
Is this some classical lemma or what?
No, there was a paper. I don't exactly remember it now. Yeah. And so using that and the fact that the sum of the absolute values of the coefficients of g is at most p to the power k, we get this lower bound. So now I'll just briefly state what a property tester is. So it is basically a class. So property tester is an algorithm, and let's say we are given a class of functions C. So and also given access to the truth table of a function f of a Boolean valued function. Then whether f is in C or if is epsilon far from C, the algorithm tests that with success probability some greater than equal to 2/3. And the number of queries made, to the truth table of f is the query complexity. Okay. And so a function is epsilon far from s-sparse Boolean if if for every s-sparse function, if s-sparse Boolean valued function g, the L2 distance between f and g is greater than equal to square root of 7. And so by L2 distance, I mean probability that fx is not equal to gx. So L2 distance that we already know, that one and this one are actually related up to some constant. Okay, and this is the theorem that we showed that any non-adaptive so there is a, so for a fixed prime p, there is a non-adaptive polynomial s1 by epsilon query algorithm, which tests whether a function is s-sparse or it is epsilon far from s-sparse. And so a finite Abelian group is not a vector space in general, and so the proof technique and also the proof techniques of Gopalan uses a lot of properties from vector space. And and it is also not known yet whether they can be done for ZPM to the power n kind of structures, where n is strictly greater than 1. And so it still remains open that whether this can be generalized for Abelian groups.
Let's go back.
Yeah, sure.
E to the m to the n.
So previously we had seen the ZP to the power n, so m was equal to 1, where the vector space structure was there. But in this case, we don't have the vector space structure because n is strictly greater than 1.
No,
So
but
it is a
Z p to the m, you're talking about.
Z4, Z8, and also Z9.
That is integers modulo 4, modulo 8. Is that what you are referring to, or what is Z4, Z8 refer?
Yeah, right, yeah.
Z mod 4.
Z mod 4, yes.
Yeah.
But why do you get? Doesn't the kind of Abelian theorem always give you? You always get. Why will you get one? Why will you get what? Don't you always write it as primes? No. Oh, you will always get the prime group or not? Yeah. You're also.
I missed something. So your previous was not for this.
No, it was for ZP1 to the power whole to the power n1 plus ZP2 whole to the power n2. No. Yes.
So in the Abelian group decomposition, you only get the prime group. You cannot get the prime power group.
I mean, for that case, you don't have.
Right, so, sorry, where exactly does the, I mean, if you instead of p you had p power m, like where in your proof does it fail? Does it fail because of this? The complex number value bound algebraic number theory resulted?
No, actually, so there's a so there is a thing. So we need to find out or get an upper bound. I think, upper bound on number of solutions to set of equations.
Okay.
And that we don't have for Abelian groups. So actually, we have tried something. So not sure whether that will work. So I'll discuss it. Yeah.
More questions?
That's done.
We have used this Hensel-Dicting kind of techniques. And so I have done something that we actually need to check whether that works